Hello everyone, welcome to my YouTube channel. So today I'm going to discuss an interesting fact from real analysis, which is how to check Riemann integrability of a function. Integrability of a function. So what do I mean by that? Suppose if from closed interval a comma b to r be a function, how can you check? Function? How can you check? Say bounded function. How can you check if is Riemann integrable? Okay. So this video I am going to make for the student of BSc Mathematics, because those who have already seen measure theory, they know that how to check this and they know everything details about this concept. So but most of the students who are from BSc, they don't know, so that's why I'm making this video. Okay, so here I am talking about the definition of a measure zero set. Okay, so a set of measure zero or null set. So a set F of R is called null set, or a set of measure 0 or a set of measure 0 if for any epsilon greater than 0 there exists a countable collection of open intervals I1 I2 ... such that F is contained in union of I1 I2 up to infinity and summation L of I equal to 1 to infinity less than epsilon. For every epsilon this should happen. So for every epsilon you need to find a countable collection of open interval depending on that epsilon. So here depending on the epsilon, such that this happens. Okay, so what do I mean by length of an open interval? So length of an open interval is basically, suppose your I is defined as a comma b, then length of I is b minus a. Okay, so that means a set of measure 0 or a set or a null set is basically, for any epsilon greater than 0 you can find out a countable collection of open intervals such that F is contained in the union and summation of length of that open interval is then. Okay, fine. Now an important theorem A for any bounded function F from closed interval a b to r, F is Riemann integrable if and only if set of discontinuities of F has measure 0. Measure 0, or I should write it has measure 0 or it is null set, right? If you have any bounded function from closed interval ab to r, then you can say it is Riemann integrable if and only if, this is if and only if condition. That's why it is important. It's a very, very important theorem. If and only if set of discontinuities of f has measure 0. That means if you just check this, then by checking this you can give answer of any question coming from this Riemann integrability part, right? You don't need to use lots of different theorems. You can deduce every theorem you know related to this Riemann integrability from this theorem. Like so, like let's do some example. So first of all, okay, so set of measure 0 sets properties. Okay, properties. Okay, by the way, I am not going to give the proof of this theorem because this proof of this theorem requires some lengthy proof, so then the video will be very long. So that's why if you are interested, then you should definitely check this proof. You can just search in Google, you will get enough reference and you can check the proof. The proof is simple, just by using basic real analysis fact you can do that. Okay, so this is fine. And also you can check some properties of the set of measure 0 set or null set. So property is a subset of a null set is also a null set, right? And this is simple to prove. And a countable set has measure 0. Okay, these two properties are very important properties, and there are other properties also, but you need these two properties. These two are very important properties. Okay, so let's say now let's give some example of Riemann integrability, right? So first thing, you know that if if f from a to b r has finitely many discontinuities, then f is Riemann integrable, right? So that means it is equivalent to show that finite set has measure 0 or a finite set is null set. So from the above property, you know that a countable set has measure 0 and any subset of a measure 0 set is of measure 0. So you can take any countable set that has measure 0 and you can take any countable set which has a subset of this discontinuity. Okay, so finite sets are subset of this countable set, so that means finite set also has measure 0. Okay, in this way you can deduce all the results you have seen in real analysis. Okay, let's give some different example. Okay, so very important example, important, that you know that I think you know that if f from 0 1 to r fx equal to 0 for all x belongs to q, so all x belongs to q complement, and fx equal to 1 for all x belongs to q, basically characteristic function on q. Okay, so you know that this function is not Riemann integrable. This is called Dirichlet function. This is not Riemann integrable. Why this is not Riemann integrable? Because this is not Riemann integrable because see, the discontinuities d of f is the entire closed interval 0 1, and this is not a set of measure 0. Okay, this is not a set of measure 0. You can see that. Okay, you can prove by that definition. You can't for every epsilon you can't have that. Okay, such that this. Okay, in particular you can take epsilon to be half And you can see that you can't write this set as a subset of union of open intervals such that the summation of that interval is less than epsilon, in particular less than half, because even if you can do it for any epsilon less than 1, okay, for particularly this case. So that's why this function is not Riemann integrable. Okay, you can prove it via the definition of Riemann integrability, but that will take a long time. But if you know this theorem, this is a very strong result and a very big theorem, so then you can say directly that this is not Riemann integrable. Another example, which is a very interesting example, that is popcorn functions or Thomas functions. The function is given by fx equal to, say f is 0 1 to r, fx equal to 1 by q when x equal to p by q, basically x is rational, and 0 when x not in q, I mean when x is in q complement. So you can see that, and you have already seen, and you should prove it, that set of discontinuity of this function is 0 on intersection q, right? So at every irrational number this is continuous, but at every rational number this is discontinuous. So df is 0 on intersection q, and this is a countable set. So df is countable. df is countable. So that's why, since any countable set has measure 0, so that's why it is Riemann integrable. So but if you want to prove it by hand, that by just estimate upper like upper Darboux sum and lower Darboux sum, and that's all, or Riemann sum concept, then it will take a very difficult work to prove. So that's why it is a very interesting a, a result, and also very important theorem. So since df is countable, so that means it is Riemann integrable. You can check it. So that's why if you have any function, you can check its discontinuities, that you can find, because you already know real analysis basic part, and you can easily do that. And then you can say it is Riemann integrable or not by just looking at its set of discontinuities. Okay, so another very important result, you know that any monotone function is Riemann integrable, right? So you know that any monotone function on AB is Riemann integrable, right? But this you can prove by, again, same, because you know that any monotone function has discontinuity at most countable, right? So you know that any monotone function has discontinuity at most countable. That means, again, the set of discontinuity forms a countable set. Then this so that's why any monotone function is a Riemann integrable function. Okay, so these type of questions was asked in my interview of TIFR Mumbai, and in the last part one of the professor asked me a very interesting question. I think you should ask me that question also, because here everything, whatever I am giving the examples, in that examples the discontinuities are either finite or at most countable, right? So the natural question can occur, that does there exist a function, uh, or does there exist a function whose set of discontinuities is uncountable, but also it is Riemann integrable? Or in other words, does there exist a function, does there exist a subset of R which is uncountable but a null set? Okay, so a very important thing, does there exist a function, say 0 1 to R, such that f has uncountable many discontinuities, but f has but f is Riemann integrable. Okay, this was the exact question asked to me in TFR Mumbai interview. So this is a very important question. Okay, and see, then that, and I gave the answer. Yes, there exists as a function. Okay, in particular, so that means it is enough to check. It is enough to find a first. It is enough to find a set, a subset 0 1 having measure 0. So my measure 0 and it is uncountable. So my idea was that, because I know that this result holds, right? So if f is Riemann integrable, that means if I need some f which is Riemann integrable, that means set of discontinuities must have measure 0. But according to the given condition, the set of discontinuity must be uncountable. So I need to find the uncountable subset of closed interval 0 1 which has measure 0, and that you can find, that is Cantor set. Okay, now it is a very important exercise. Okay, this is your exercise to show that first thing is that Cantor set is a null set, and then characteristic function on Cantor set satisfy the question star. Okay, if I write it as star, this star. Okay, so this characteristic function on Cantor set, what do I mean by characteristic function? So the fx is 1 if x belongs to Cantor set, 0 otherwise. Okay, so closed interval 0 1 to r. Show that this set of discontinuity of the this set is Cantor set itself, and then another thing, you should show that Cantor set is a null set. Then combining these two, you will get this answer. I hope this video is going to be helpful to you all. Now, whenever you will get any questions related to Riemann integrability, that whether this function is Riemann integrable or not, try to use this theorem. This theorem is going to be very helpful, and you can use this, and you can also get the answer very fast. Okay, and if you are interested, you should definitely see the proof of this theorem, which is very nice, and that will help you to learn many things. Okay, try to apply this theorem. This is going to be a very helpful theorem. Thank you.